Hello, today we're going to talk about reactivity 3.3.2 and 3.3.3. This is all about free radical reactions. So we're going to start with homolytic fission and then talk about free radical substitution. So let's start out talking about homolytic fission. Homolytic fission is when you are breaking a covalent bond, but you're breaking it in such a way that both atoms get one of the electrons that's being shared. That's why it's called homolytic, because they're both getting the same number of electrons. This can happen either in heat or light, and typically it will be using UV radiation so that it has enough energy to break that bond. But if it's heat, we say it's a thermolytic process. If it's in light, UV light, we say it's a phytolytic process. And for the most part, we're going to be talking about homolytic fission in regards to the halogens. So let's talk about chlorine. So diatomic chlorine looks like this, with 2 electrons being shared in that covalent bond. And then if it's happening in heat, we could write heat over the arrow. Or if it's happening in UV radiation, you'll see the UV like that. And for the most part, we're going to be using UV radiation. Sometimes I've also seen light, just saying light, distinguishing from dark. If it was in the dark, nothing would happen. So in this case, you would wind up breaking the covalent bond between the two, and both of the chlorines would turn into a radical product. So they would each get 1 electron from the bond. You also need to be able to show the mechanism of action, so showing where the electrons are going using single barbed arrows. So let's look at that. You would have a curly arrow with just 1/2 of the arrowhead, and then a curvy arrow with the other half, like this. If you use a complete arrow, we would use that to represent a pair of electrons moving, which it's not doing that. You have each electron going separately. So that's why you have these fishhook or single barbed arrows. One thing that I would like to point out is if you're using bromine, you can tell if the reaction is happening or not, because bromine liquid is kind of a orange-brown color. So if you have it in light conditions, it will break down into bromine radicals. Like that. But you'll have this orangey brown color, and then it will turn to colorless, typically. But then if you were to change it to dark conditions, you would still see that brownish orange color because no reaction would happen. Another way that you can write this out as a chemical equation is, instead of drawing like the Lewis structures, you would have the Cl2 in UV or light forming 2 chloride radicals, or Br2 in UV, you'd get 2 bromine radicals. Okay, so now when we start talking about the chemical reaction involved, I want to remind you of the difference between thermodynamic control for chemical reactions and then kinetic control for chemical reactions. So let's look at a energy profile diagram. So these are reactants and products. Typically, exothermic reactions tend to be more thermodynamically favorable. Of course, entropy also plays a role in that. So in this case, though, if if there is a release of free energy, delta G is negative, then it's going to be thermodynamically favorable, or a spontaneous reaction. But remember that thermodynamics doesn't tell us anything about speed, doesn't tell us anything about kinetics. So kinetics is going to be influenced by a lot of different things, but one of the big things if we're looking at energy diagrams like this is the activation energy. If the reaction has a really high activation energy, then it's going to be a very slow reaction, and it might not even happen. So you have to have enough energy to be able to get over the hump, right? To be able to start the reaction, whether or not it's thermodynamically favorable. So those are always the two things that are involved. Is the activation energy here compared to the overall, whether it's gaining or releasing free energy. So that's what we need to consider in this case. For free radical substitution reactions, they're going to be thermodynamically favorable, but they tend to have very high activation energies. So in order to get that homolytic fission to happen, you need a lot of energy. That's why you need like UV radiation or very high heat. But once you get over that activation energy hump, then it is a favorable reaction. So the overall process for free radical substitution, you're always starting with an alkane of some kind, and we're typically going to have a halogen of some kind. It could also be like a hydrogen halogen, like HBr or HCl. But most part, you're going to have a halogen reacting with an alkane. And the first step is going to be initiation. And our initiation is going to be that homolytic fission that we talked about. So you need to break a covalent bond and form your free radical products. The second step in the process is called propagation. So let me start in with an example here. If I have chlorine forming two chloride radicals, like that. Propagation then is where one of the free radicals reacts with the alkane. So let's say we're doing, I don't know, ethane, so C2H6. It's going to form a new radical. So typically you'll see like C2H5 and a product that is not a free radical. So again, your reactants are always a radical plus a non-radical is going to make a new radical and a new non-radical. And typically you're going to see the hydrogen moving. Now, this can happen a number of different times. As long as you have enough radicals to react with enough non-radicals, it's going to happen. Eventually, you need to terminate the reaction. So termination is the third step. And that's where you're going to take two radicals, so could be your other chlorine, and maybe this new radical that we formed. And they're going to come together and make your product. So you'll have a radical plus a radical gives a non-radical. So the net reaction here is the chlorine plus the ethane forming the C2H5Cl plus an HCl. But it has to go through these steps, these three steps, in order to form that. Okay, so this example says to use curly arrows to illustrate the homolytic fission of the covalent bond in iodine. So we have our two I's. And the curly arrows, we need to make sure that we're showing just a single barbed arrow because only one of the electrons is going to either iodine. And then you're left with two iodine radicals. And we can summarize that as I2 goes into two iodine radicals. Okay, so what are the three stages of radical mechanism? We have initiation, propagation, and termination. But then it says use the reaction of methane with bromine to explain your answer, giving relevant equations for each stage. So I'm going to abbreviate I for initiation. So in this case, we're going to take the bromine, and it's going to undergo homolytic fission, and we're going to assume that it's UV conditions in this case, but it could be heat, and you're left with 2 bromine radicals. Now for propagation, this is where one of those bromine radicals is going to react with methane, CH4. And in propagation, the radical, you're forming a new radical and a new non-radical. And so typically that involves the hydrogen moving to the halogen, and then you're left with some kind of carbon radical, organic radical. And then our last step would be termination. And in this case, the other bromine radical can react with this CH3 radical that we formed here. And termination is always 2 radicals coming together to form a new product, like this. And so our net equation is the Br2 plus CH4 forms HBr plus CH3Br. Okay, so this one connects to reactivity 1.2. Why do chlorofluorocarbons in the atmosphere break down to release chlorine radicals, but typically not fluorine radicals? So if you have a carbon and it has fluorine or chlorine attached, that bond is going to have to break in order to release free radicals. So which bond is easier to break? Well, it's going to be the carbon-chlorine bond is going to be easier to break. So you're going to be left with the carbon with fluorine and then the chlorine on its own. And that's has to do with a couple of different things. One of those being fluorine has a really high electronegativity, so it's going to kind of hang on a little bit stronger there to both of the electrons instead of a single undergoing that homolytic fission. Another thing would be that the bond between carbon and chlorine is a longer bond because chlorine has a larger radius. So again, it's a little bit easier to break because of that longer distance. So in structure 2.2, what is the reverse process of homolytic fission? Well, if we think about the forward reaction, which is really initiation, right? I'm going to use bromine. You're forming 2 bromine radicals. The reverse reaction of that would be to take the bromine radicals and add them together to form the Br2. Well, this is effectively a termination step where you have 2 radicals coming together to form a non-radical product. So that could be, you call that combination. Some people call that synthesis, where you're combining the 2 separate elements into one. But it's effectively a termination step because you're eliminating the radicals. Now this also links back to structure 2.2. The chlorine radicals that can be released from the chlorofluorocarbons that we talked about, they're able to break down ozone, but not oxygen. What does this suggest about the relative strengths of bonds in the 2 allotropes? So ozone has resonance like this. That's one resonance structure for ozone and the other resonance structure for ozone. So those 2 electrons that are in the pi bond are able to move between both locations. They're delocalized. So the bond order is actually about 1.5 for the bonds in ozone. So because they're about 1.5, they're easier to break and they're longer than the double bond that is present in just O2, which just has a double bond and is shorter and stronger than the roughly 1.5 bonds in ozone. So I would definitely know the resonance structures for ozone. You can, figure them out the day of if you need to, but ozone pops up enough as an example that it's it's worth just knowing the resonance structures for it. And then this also links back to reactivity 2.2, why are alkanes described as kinetically stable but thermodynamically unstable. So alkanes can react, they are reactive, but they have a very high activation energy. So that's why they're called kinetically stable, because it takes a lot of energy to get a reaction started with an alkane. But they have a relatively high energy when we're talking about our reaction profile here. And so this would be where the alkanes, and this might be a halogen alkane produced from the free radical substitution. So pretty high activation energy, but it winds up being thermodynamically favorable overall because there's a release of free energy. And your products wind up at a more stable state energetically.